Good morning. This is Unit 3, Day 4 notes. We're going to go over properties of logs, more properties of logs today. So the product property is if we have a log with base b of m times n, then we can expand this, and this will be log base b of m plus log base b of n. Okay, so the quotient property for is log base b, we'll say m divided by n. Just remember when we're dividing, that's subtraction, so that'll be log base b of m minus log base b of n. The power property is pretty cool. We have log base b of m to the p. This is going to be our function. We can bring down the p, and this is the same as p times log base b of m. Expanding a logarithmic expression like this, we can say this is log of 8 plus log of x plus log of y to the 4th power. And I can keep expanding this. I know that 8 is 2 cubed, so this is log 2 cubed plus log of x. I cannot do anything to this x. But whenever I have an exponent, I can bring it down in front. That's the power rule. So we have 4 log of y. And now my last step is going to bring this 3 down. So this is 3 log of 2 plus log of x plus 4 log of y. Alright, let's try this one. This is a square root over the whole thing. So I cannot separate this underneath the square root. So I can separate the fraction log x squared plus 5 to the 1/2. I'm just making the square root an exponent. And then this fraction means that we're going to have a minus log of x. I'm going to bring out the fraction, which will be 1/2 log of x squared plus 5, and that's all I can do, minus log of x. That's it. Alrighty, go ahead and keep going. We're going to do condensing the logs. So we're going to go the opposite way. Whenever I see a minus, I know that this is going to be a fraction. So this is natural log of x to the 5th divided by the 2 goes, and it's an exponent. The 2 in front of the natural log becomes an exponent. So this is going to be xy squared. All of it is squared. Usually we'll simplify this, and this will be natural log of x to the 5th over x squared y squared, because we can cancel these. And this will be natural log of x to the, when we're dividing, we're actually subtracting the exponent, so 5 minus 2 is 3 over y squared. Okay, this is simplified, condensed. This one's pretty easy. Let's try this. 3, we have to bring up to become an exponent, so this is natural log of x cubed y, all of it, to the 3rd power. And then we're going to bring this one up too. So plus natural log of yz, all of it, to the 2nd power. We have to remember to distribute these powers. So this is natural log of x to the, when we have a exponent to another exponent, we're actually multiplying them. So this is to the 9th power, and this is y to the 3rd power, plus natural log of y squared, and then z squared, alrighty, oh, this is already squared, so this is going to be z to the 4th, squared to the 2nd power is to the 4th power. Now this plus means we're going to multiply. I can condense it one more time. So I have 1 log, natural log, of x to the 9th, y cubed, y to the squared, z to the 4th, And then when I'm multiplying the bases, I add the exponents. So my last log will be x to the 9th, y to the 5th power, and then z to the 4th. And that's it. Go ahead and turn your paper over. This is the change of base formula. So if our calculator, we can't plug in a base to the 1/2, or they ask you to change your base, we have a formula for this. This is log base b of x. Okay? If we want to change this base, it's going to be log of the big over log of the small. So log of the expression, maybe the expression of this one is x, divided by log of the small, which is the old base b. Now this log can be any base you want, but it has to be the same one. So I'm going to make this a, so you guys remember. We can even make it just log base 10. So this would be log base 10 of x. We don't write a base if it's base 10. And then log base 10 of b. It could be even natural log. If we want everything to be natural log, everything else in the equation is natural log, we're going to make it natural log. Natural log of x over natural log of b. So the log has to have the same base, so you can make it any base you want. So let's try this. We're going to change the base of log base 3 of 13. I'm going to make it a base 10. So I have log of the big, 13, divided by log of the small, the old base was 3. And this, I do not know what this is. You're going to have to plug this into your calculator. You're going to get something like maybe 2.335. Try it out and make sure I'm right. Let's do the fraction, because these could be tricky just looking at it. So we have log of the big, log of the expression, which is 2, divided by log of the base, which is 1/2. You guys can put 0.5 if you'd like. This is also a calculator question. This is not something you're going to have to know, but log of 2 divided by log of 0.5, this is going to give you -1. Try it out. They're just going to ask you to graph the log function. We did this in our last notes. We said that this is my vertical asymptote. It goes through this point, 1, 0, and remember the logs have a vertical asymptote, exponentials have a horizontal asymptote because they're inverses of one another. My domain for log is 0 to infinity. My range goes all the way down to -infinity, and even though it looks like it has an asymptote, it doesn't. It goes all the way up to positive infinity. So I'm going to say -infinity to positive infinity. It is continuously increasing on the total domain. There is no symmetry, so it's neither even nor odd. I'll put none. It's bounded. It goes up forever, so it is actually unbounded. It says local extrema, so this means is there a max or a min? There is none, so I'm going to put none. My horizontal asymptote logs do not have a horizontal asymptote, but they do have a vertical asymptote. It's usually going to be the y-axis. That's when x equals 0, unless there's some shifting going on, but this one's just a basic log. The end behavior, we're going to use limit notation. This is new for us still. As x goes to infinity means to the right, and then the limit as x goes to -infinity means to the left. This one actually doesn't. Logs don't go to -infinity, they go to 0. So that is going to be towards that asymptote. So our function, as x goes to the right, it's going to go up infinitely. So this is infinity. Our function, as we approach this asymptote, we're going to go down. So it's going to go to -infinity. Down means -infinity. So what I did is I just graphed your function f of x, a natural log of x for you. Remember, it goes through 1, 0. The transformation, actually this with the base 5 will go through 1, 0 also. But tell me if it goes up over or under. You can graph it on Desmos. The 1/2 is actually pretty cool. Since the 1/2 has to be to a negative power to give us our x, you're going to actually flip it across the x-axis. So we're going to reflect it across the x-axis, and it's still going to go through this point, and it's going to look like this. So this is my h of x. Wanted to help you guys with this one. Alright, this is going to be the last thing that we're going to do. This is a log model. Fit the log function to the data. Remember, we can use our calculator for this. Okay, so what we're going to do is we're going to get out our calculator, and we're going to go to Stat, and we're going to go to Edit, so we can input these numbers. On the first row, I put the 2400, 2100, 18, 16, 14, 13, 11. And on the right-hand side, the L2, I put 148, 160, 166, 173, 178, 182, 193. And what we're going to do, it says, the directions say, to fit a logarithmic function to the data. If you even try the other log, the logistic, we're going to go back to Stat, and then you go to the right for Calc. And if you even try going to B, logistic, it's not going to work. It'll give you like error or something. But we have a natural log, or LN regression. It's not line regression, it's LN regression, so it's number 9 on mine. And I'm going to press enter, enter, enter. It's a lot of enters, and then what we're going to get is y equals 569.7544. So when we put 754, right? Oops, I don't know why it's changing. Minus, I think it's negative, so B is negative 53.91 or 907. So minus 53.907, and then ln of x. Okay, I'm sorry, it kind of overlapped. Okay, so this is my data. Use a function above to find the number of personal computers that would be demanded if the price was $1,500. So my price is going to be $1,500. I'm going to plug it in. What is the quantity when we have 569.754 minus 53.907 natural log of 1,500? This is my x's. I made this like my domain, my x values. So the price is going to be still an x value. So I'm going to plug that in, natural log of x. And what I get is, just plug this into your calculator. You get something like maybe 175.5. I would actually round this to like 176 computers, because we can't have half of a computer, and 5 and above, give it a shove. Also, if you're talking about people, you usually round it up or down. You can't have a half a person, so, either way, depending on how the question is worded. Alright guys, this is the last one I'm going to do today. If you have any questions, please ask. Have a wonderful day.